method. Okay, normally the people will use the method which is available in the laboratory, which we know to use, right? And which is, it is available. And my supervisor or someone knows to use it, so I use it also. But very frequently, when the people talk about the deposition method used for their work, we always want to say that we have advantages over other methods, okay? And if you look to the industry, we use many different methods. Even if you look to the clean room technologies, we use CVD, plasma CVD, ILD, sputtering, evaporation, and so on, okay? So there is no one method, magical one, and if someone is telling you that this is a nice method, is only advantages, it's a publicity, okay? Because frequently advantages in one case is disadvantages in another case, okay? So you have to keep a critical mind. By myself, I was grown by CVD community, okay? And today I will talk about CVD, but no way today I will say you that it's the best method. It has a lot of possibilities, it's a very versatile method, but is not really the best, because it doesn't exist the best method. No one wants to work today. Okay, so the outline, so I will talk about the CVD system, what is the CVD in general, then the precursor delivery systems, the CVD phenomenon, different mechanisms, thermodynamics, kinetics, homogeneity of layers, then how to, if I have time, because I lost some time at the beginning, if I have time, how to control volatile components, volatile oxides, for example, in the layer. And the last part is going to be about epitaxy, but it's very general. It's not something related to CVD. Okay, what is a chemical vapor deposition? Chemical vapor deposition, basically, it's a method which implies chemical reaction, chemical surface reaction between volatile molecules. Okay? So what is important is a chemical reaction, which just comes in the name, okay, and the vapor. It means that we are in the vapor phase, our molecules are volatile, and on the surface they will react. Okay? But be careful, the molecules, they do not react with the substrate. Okay? They react in between them to form a compound. They will create a link bonding to the substrate, but they do not react chemically with the substrate. Because if your precursors start to react chemically with your substrate, your layer is dead. Okay? Yeah. So basically we have a volatile, we have some sorts of precursors, molecules, which are vaporized or in vapor phase, and then it comes to the substrate, and then we have a deposition. So very simple distinction. Right? So when the precursors can be initially at different states, can be gas, can be solids or liquids. Right? So we have in all CVD systems we have like the main part. So we have a evaporator or our vapor source. So if we have a solid or liquid precursors, we need to evaporate them to create a vapor. Okay, so we have an evaporator or just a gas cabin. Then we have a deposition chamber. So in the evaporator, the temperature has to be higher than evaporation temperature of the compound to create a vapor. Right? In the deposition chamber, the temperature is always higher than evaporation temperature, because we need to decompose the precursors, and this temperature has to be higher than the decomposition or reaction temperature. Okay? So basically, this depends what kind of precursors we use, and this one also depends on the precursors, but also the temperature we choose with respect to what we want to grow. Do we want to grow epitaxial films? Do we want to grow polycrystalline films, amorphous, and so on? So this deposition temperature is dependent not only on the precursors, so this temperature has to be higher to decompose, but it also depends what kind of quality of the layer we want to get. Okay? And then afterwards is a chemical vapor deposition, so when we have chemical residues, which frequently are not so nice and can be even toxic and so on. So the security in chemical methods is very important. It's not like in physical methods. In physical methods, it's okay, you can put in any room and so on. So normally around with chemical reactors, we have extractors and so on to extract everything and to protect the users, and also not to extract everything to outside. In the laboratories, normally it just goes to extraction and then outside, right? But in In industrial reactors, normally we have like a treatment of residues to stop everything not to flow out to nature. Okay? Yeah. So then we have like two types of reactors, which we call differential reactor. It means that the precursor concentration is constant in the reactor, or starved reactor where you have strong gradients, fast reactions. So it means that everything reacts. Right. So this is just one example of many, many different systems which exist already in commercial scale. So basically we have this precursor generation of the gas control system, an operator, and so on. Then we have reactors, which is placed in the glove box. In this case, it's not necessarily in the glove box all the time, but in semiconductor technology, we use glove box to avoid any oxygen coming in. So all the reactor, everything is manipulated in the glove box. But if you are outside community, you don't care, you don't need all these glove boxes, everything can be open, you don't need extra vacuums inside, and so on. Yeah. And then you have a control panel, and then also the treatment afterwards of all the reaction products. So basically, CVD can be done by using several types of reactions. I will not go to details, but just to show you that, for example, we can use pyrolysis with decomposition. We can do reduction by hydrogen. Normally, we use hydrogen to reduce the compounds. So basically, you see that at the beginning, we have a gas, right? And in the reaction, chemical reaction, we always have one compound which becomes solid, and other compounds have to remain gas also to leave out. Okay, so it's only our part which is interesting for growing the film has to be solid. Okay. So the reduction by hydrogen normally, and you see, for example, this is two reactions used for silicon grown layers. So for amorphous layers, we use just pyrolysis, a low temperature process, and then, for example, one crystalline layers is much higher temperature, and we use another type of reaction, which is more like reduction. So then we have oxidation, which is very interesting for oxides. So yeah, so basically you put oxygen, ozone, or carbon dioxide with hydrogen and so on. You can put quite complicated reactions inside. Right? You can use also reversible reactions, where you can get a solid on this side, but you see, for example, on this side it goes at 750, you can go to gallium arsenide by using this reaction. But if you increase more temperature, 850 is reversible reaction, your gallium arsenide will become gas. So you need to be careful also not to use too high temperature for this type of reactions. Yeah. So when you have formation of compounds, you have more general, where you can from carbides, nitrides, oxides, and so on. So there are many, many different reactions which are used in industry and laboratories and so on. So, and today I'll talk mainly about metal organics, but I want just to make a difference between organometallic and metal organic. Okay? Organometallic precursors, it means that we have an element or metal ion, right? And this is connected directly to the carbon. When you have a direct link to the carbon, we call organometallic. And then you have a link between the metal and the oxygen or nitrogen, which means not directly linked to the carbon, we call metal organic precursors. Right? So for oxides, we use basically oxidation reactions. So oxidation by oxygen or ozone, which is more efficient in oxidation. And this is compound formation. So normally in CVD we will do with multi-element compounds, and in this school I saw a lot of different compounds which you study, you are growing and so on. So basically we will use the metal organic precursors, okay, of different elements. We will put together all them, and we'll put some oxygen, we'll evaporate everything, and we'll send to our reaction zone, and then we can form multi-components. So we have the big freedom in the composition on what type of compounds you will grow and so on, how much you will dope, what kind of composition is going to be. Me personally, I'm working about 18 years in CVD, and so I was growing all these different materials by CVD. So it's quite flexible to go from one material to another one and so on. But these CVD metal organic precursors are mainly used when you use these multi-compounds, because it's very complicated to find a molecule with hydride and so on, and to react all together and so on, and to be gases. So usually we use always metal organic precursors. That's from where comes the name MOCVD. Right? And as all these compounds, they are organic compounds where volatility temperatures were quite close. Not necessarily close enough. So we need to choose a precursor, but where volatility is quite similar, and then when you need to break them down, it's organic molecule. So basically when you go more than 400, 500 degrees, it definitely will burn out. So, and then you get out CO2 or carbon dioxide, carbon monoxide, and so on. It's just running water and so on. And everything goes out and it remains only oxide. So normally these reaction mechanisms, what kind of molecules you get at the end, no one knows. Okay, there is some in situ analysis and so on, but normally we just don't care. Okay, so we put metal organic compounds, we put oxygen, we give it temperature, everything burns, and you get oxide. This is the principle of that. Okay, so the first part, which is very important in CVD, is the precursors and vapor delivery systems. It's the first critical part. If you don't control this part, you cannot do anything else. This is your starting point. Okay? So there are many different metal organic precursors. Alkyl, anhydride, alkoxides, aminate, cyclopentadiene, neodecatonate, alkyl, and so on. Many different molecules. And there are a lot of research groups working on that. And industry, very strong industry also on metal organic precursors. So you can buy and you have a big choice. You often have many different precursors. So basically how we choose a precursor. Because normally you have for one element, you have a list of different. So first thing is important is to be high purity and high yield. Then it has to be efficient. Then it has to be stable at ambient temperature. Because if it's already not stable at ambient temperature, then you are really in trouble. It would be good if it can be stable also in the air. Okay? So because when it's produced, when it's coming by post and so on, it's quite complicated. So, but normally anyway, all the precursors we manipulate in a glow box to be sure that there is no some changes, decompositions, and so on. It should be easy to handle and it has to be non-toxic. When we talk easy to handle, it means, for example, no burning, because some of them are pyro. So you just put some oxygen, something like this, and then get flames. So it can be quite dangerous compounds. Okay? Then it has to be concrete volatilization, so it means volatilize everything very nicely. Okay? There is no one part of the precursor is volatilized and then something is remaining. And it's important to have a significant temperature difference between evaporation and decomposition. Because once you vaporize, you need to bring the precursor to the deposition zone. And the deposition zone, the temperature is much higher. So you need to be sure that it's not start to decompose very quickly after evaporation. So it has to withstand some temperatures. Yeah, so basically industrially, mainly the family, which is but others will use as well. The main family is beta-decatonates. So it's a precursor which has 2.4 deionate group, and then all the different names that depends what you attach to them, what kind of group you are attaching. And then it will play a lot of on volatility for mass and so on. So we have a big family of beta-decatonates, and they are the most popular in research and also in industry. Yeah. So if we look now at the precursors for CVD, in what state they are normally. So it's very comfortable when you have precursor already gas formed in room temperature. Then you just connect, you send. This is, for example, all the silicon deposition and so on. So we have gas precursors, we just connect, so you don't need evaporators. The systems are much more simple. But as you see, many others will exist in solid or liquid only form. So basically, as I said, if you have a gas precursor, everything is nice. You just put a flow meter, you connect the gases, you can control the flow, and it's done. And then you have the deposition zone. That's it. Right? Then you have a solid precursor, so very old systems, and you can still see these type of systems in the laboratories. So we put in some boats, the powder, when you put in the evaporator, when you heat up and the powder evaporates, right? And then you have a flow of the gases, which comes, right? And it brings these precursors to the heating zone, to the deposition zone, which is the high temperature zone. So when you get a little bit in a trouble, then you have two precursors, and they're normally not exactly the same evaporation temperature, right? So normally we propose, for example, you have several lines, several evaporators, and then you have gases flowing and then bringing everything together. What is important in this type of systems, because as I shown in the picture, all we just heat here, we evaporate and then goes everything to the temperature everywhere here, in all the way, has to be controlled. It means the temperature cannot be low, because we'll get condensation of precursors, and it cannot get somewhere very high, because then you decompose the precursor. So it means until we zone, the ideal case, which is very difficult to do in practice, your temperature has to be as evaporation temperature. Right? Everywhere, for example, if you evaporate at 250 degrees, everywhere you keep 250 degrees, all the way. Okay? And then you bring everything to the deposition zone. So now the question is for you. Oh, very nice. I will not see your answers. But anyway, so the question, okay, so your evaporation temperature is 250 degrees, and the deposition temperature is 750 degrees. So, in which place you have a tubular furnace, right? So you evaporate your precursors. In which place are you going to place your substrate? At the entrance of the furnace, in the central part of the furnace, or up at the end of the furnace? Where is the best position, the most efficient position? Maybe I will see here, but I don't think I can see. He said I don't see your answers. I just thinking if I reverse, because sometimes I can see here, but when I cannot see here, but we can see all the questions, so maybe I can see your answers. Okay, try to respond. I will just try to do one trick. I can see answers. Okay, just wait. I need to get out this friend. Okay, up. Okay, you can see the question, I can see your answers, but you cannot see your answers. But anyway, so most of you think it's a central position, right? 18% entrance, 21% end of furnace. Okay? So everyone thinks here. And I pick a picture from the paper, right? This one. This picture is not my picture, so someone did me some paper. Never put your substrate in the middle of a furnace. Never. It's the biggest mistake. And if I put this question to this lecture, because I saw many students doing that in the lab, in my lab of CVD lab. And it's very, very wrong way. You know why? Because the temperature here is high, but temperature is high here already also. So your precursors, when we come to the furnace, they start to decompose. And if you put in the middle of a furnace, nothing will be left on your substrate. Everything will be decomposed on the walls, right? So you need to put your substrate really at the entrance of the furnace, okay? But don't forget to put a thermocouple also respect to your substrate, okay? Because if no, your temperature will be not correct, okay? So normally you put the thermocouple which touch your substrate holder, right? There's your substrate, and you put your substrate like few centimeters at the entrance from the furnace. Then it's important not to overheat your furnace, but that's it. But you have to be efficient. You have to have very strong. You have to have very strong gradient. Okay, very strong gradient here. There is no time for precursors to heat up and to decompose in the gas phase, in the volume. Okay. So you have such strong gradient that precursors will come, they touch the hot surface, and then you have this heterogeneous reaction, decomposition on the surface. So this is how you will grow your film. But if you put in the middle, then everything that, or in the volume, the gases will heat up, or will grow on the poles. If it's hot hole reactor. Okay, so how we then select a precursor? So basically, for precursors, you can find thermogravimetric analysis. This is something very common. You can find the bestsellers, we give images, you can find in the papers. So a good precursor, it means you heat up, right? And everything evaporates. This is a perfect precursor. Sometimes you may have some water loss and so on, but this is not an issue. Okay? You should have a nice drop of the weight. This is the weight as a function of temperature. Okay? The bad precursor, it has like several steps. It means some part evaporates when something else evaporates at higher temperature and even starts to decompose before completely evaporating. So here it is an example of niobium. We get niobium oxide. So it means it's still not completely evaporated, and it's able already to decompose. It's not stable enough. So it's very complicated to use these type of precursors. It's possible, but it's really not good precursor. Something that you want, everything evaporates, and precursor is still stable. This is a perfect precursor. Okay. What is the problem with the solid precursors and this method to put a boat, to put a powder, and then heat up and to evaporate? What is the problem? The problem that we cannot control the growth rate at all. Because evaporation rate, it depends on the surface. Right? You see the particles, one is small, one is big, and so on. So the precursor has particle size, the grain size is not controlled. So each time we'll take new powder, will be different, and you will not control the growth rate. Another thing that is dependent on the time. At the beginning you have a lot of material, and when you evaporate, it's less of material, and your growth rate is going down. So it means you are growing it at the beginning a lot and then slowing down. So you're not growing in a constant growth rate. And also, when you keep the precursor at this high temperature, okay, so one will evaporate, but some part of the precursor will stay a long time in this temperature. And we have a problem of aging. We can start to polymerize, we can start to decompose, and so on. And it was a real issue on that. The researchers worked a lot how to overcome these issues. Right? So for example, it was an idea, some in the laboratories we used injection of a powder. So we keep everything outside at room temperature and then use powder injection. Some others we decided to put a tape on the tape to put it like a powder, like for birds. And then the tape coming to the heating zone, and then it evaporates step by step. And another idea was to use saturated stream. So it means that you put everything to the bottle, you evaporate, you saturate the atmosphere, and then you bring gases to bring the precursors. Okay? And the most advanced idea was to use fluidized bed sublimation. It means that you put here a powder, and you send the gas through the bottom, so like make a bed. And then you get the maximum homogeneity, and then your evaporation is very dependent on how much of gases you send. Okay? So basically, when you use this saturated stream, you see you can change the flow rate of the gases, but you will not change a lot how much of precursor you will supply. You don't have a control. It's quite stable, okay? But you cannot increase the growth rate, decrease the growth rate, and so on. In the case of fluidized bed sublimator, then you increase the flow rate of the gases, you get more evaporation. So it's a little bit more advanced system, and it's easier to control, but it's still not enough. In the case of liquid precursors and solutions, so very standard system is a bubbler. The bubbler in which you have a solid or a liquid precursor or a solution of solid precursors, and then you send the gases, so you can heat up if needed, this part, and then it bubbles through and it sends the vapor to carry gases to your deposition zone. So basically many precursors you can buy already in these bubblers industrially, which you can connect then to your reactor and to do the growth. So then how to introduce the liquid in a controlled way to your evaporator, which is also an issue. You can use a mass flow meter for the liquids, and then you can control, but it's not enough, because you cannot send, in CVD, is very important thing, don't send a lot of precursors with the solvent, because it's organic, you have oxygen oxides, and it burns a lot. So I saw several times, and I still have some traces on my hand, of burning of CVD system, but it was like accidents. But organics, it burns a lot, okay? And it's even explosive. So you have to be careful not to send too much. And then we started to develop these liquid systems, supply systems. It was a lot of fire, a lot. Yeah? So we need to control how much you yes.
Yeah, I see different temperatures through all the slides, and I wonder, I assume of course that it depends on which material you deposit, but I wonder which temperature typically used for CVD.
It depends on precursor, on its volatility. Some of the precursors may be volatile at 100 degrees, 150, 200, 250, 300 is more or less the limit. You don't need higher, because organics can start to decompose. So it's below 300 for evaporation, okay? But it depends, then it depends. If it's liquid, it's a gas, if it's very volatile or not, so it really depends on the precursor. And then for the deposition, so basically, I will show at the end what is concerning the temperature, but it's, let's say, above 400. Again, organic starts to decompose. But if you work on epitaxy, on things like this, then it's not your limiting where you can decompose these precursors. The limiting is that you need a high quality crystalline quality, right? So when you go to 700, 800, 900, and 1000, it depends on your material, what kind of material you're growing. So it's very, very flexible.
Yeah, because I was thinking about the industrial path where you don't have to, if you use this technique for beer integration, you don't have to cross the 500, 500.
Yeah, so I'll show you how we try to overcome these problems, but then, okay. So yeah, so basically there are several ways how you would like to introduce precursors, liquid precursors or solutions. So capillary tubes, syringes, which is very primitive ways. You put a step water and push it a little bit, it goes little by little. Then you have aerosol, CVD, normally it's done at atmospheric pressure. Right? And you can just generate aerosol and you send. So this one is very dangerous. This one left me some traces on my hand. Yeah, because if you send too much with oxygen, then it becomes a lot and it explodes. And it depends on the temperature which you're using for the substrate. Yeah. And then in '93, when it came the period when everyone wanted to develop superconductors, the people developed electrovalves. Very simple. They didn't develop electrovalves. They just took car injectors from Peugeot. It was a Bosch injector which was used in Peugeot, because this invention was done in France, in the laboratory in which I did my PhD, but I didn't do it at that time. I was very young at this time. Yeah, so we took the car injectors, and what we did, we connected to the evaporator, we connected to the computer, and then car injector injected droplet by droplet the solution. And it was very safe, because you can control, it closes each time, the doses are very small, right? And you control by computer, you see how much you inject, then you stop, what is the frequency of injection. So it was very nice on that. You can connect several injectors to inject different materials, to do multi-layers and whatever. Right. Yeah, so basically how it looks, you have a car injector, you have a bottle for a precursor, so a big stuff. You can connect to the bubbler also, right? And then it's injecting very micro doses, and then the evaporation is very efficient, because we have a solution of a precursor, and it evaporates immediately. Everything is controlled by computer. You have very nice evaporation, and it's adapted for solid or liquid precursors. So if it's solid, you just dissolve in some solvent into solution. And basically, the company, German company who bought that patent, they showed that we can control about 1 nanometer thickness of a layer, below 1 nanometer, because one post was growing about 0.6 angstrom, so we can control very precisely the growth rate. Then we developed a little bit some other systems which never came to the industry, so like to inject on the tape also. There are some systems also with like the flow meter just dropping the droplets on the tape and so on, but it's not something which is really used in industrial way. And basically then the car industry developed further injectors, because CVD community is very small. To develop injectors would be too expensive and too complicated, right, for chemists to do that. So they followed like development of the car industry, and car industry developed much more performant injectors, which is double injection and so on. And they applied that, this type of injector, so use double injection. So first injector, they inject liquid, and then second it connects to the gases, and then you have injection liquid and gases, and then you have really atomic like vapor, very spread, very tiny, very nice for evaporation. So this is this which we call double injection, and which is today implemented in industry. It's a double injection. Yeah. So basically this is industrial systems. So initially these injection systems were done by Ekstrom, but recently in 2017 they sold the technology to Korea, but the patent is already dropped 93, it's 20 years already. So it's gone, so now everyone can use. And then you have NLC systems also, which is using this type. And basically the wafers can go to 8 inches and whatever. It's just, because in CVD system it's not an issue, the surface area. Yeah. What is this? Okay. Oh. Not very high quality. Okay. Okay, so basically, so I wanted just to show one example, application example. For example, lanthanum nickel material, which I saw in some several presentations. Okay, so we would use these big beta decatonates, what we call lanthanum THD and nickel THD proportions. So basically, here we see thermogrammetric analysis. So we see that lanthanum evaporation, this one, right, this is solid line, is evaporating at slightly higher temperature than nickel precursor. And normally in these injection systems, that's why you use the same evaporator. So you need to adjust your temperatures not to be too hot for nickel and not too low for lanthanum. So it's very important to optimize evaporation temperature. And what is important when you see this thermogrammetric analysis, normally it's done at atmospheric pressure. And then you work at several torrs. So CVD is not very low pressure method, so it's about several torrs and so on. We just use primary pumps. So basically this evaporation temperature will be lower. Okay, so you know more or less your limits, but you do not expect to go higher. Okay, and then you do optimization. Very nice, you even don't see the points. Okay, what I can say. We did by two methods. So one, this is the direct liquid injection CVD system, which is industrial CVD system, which is a double injection. Right? And another system is this old system with the first viscar injector, simple injection system. So basically what you saw, that we had the growth rate until about 190 degrees by this double injection, about 190, and then it started to drop down. Okay, and the lanthanum concentration started to increase. What does it mean? That above this temperature, at this pressure, nickel starts to decompose, because lanthanum starts to, because the growth rate is increasing, so it means that the nickel starts to decompose, and that's why lanthanum composition in the layer starts to increase. In the case of simple injection system, and it's also homemade system, so it means you don't control so well all the temperatures everywhere, like in industrial system. Basically, the best temperature to get the maximum, like lanthanum nickel ratio, and to get the maximum growth rate, it was about 250 degrees. So we see to move from one system to another system is not so easy. It depends where thermocouples are placed in evaporators, how the temperature is controlled, how is the efficiency of evaporation. But definitely what we can see that in this case, evaporation is much, much more efficient when you use this double injection system comparing to the simple injection. But there's also efficiency in temperatures in evaporators. So it's very difficult to take results from one paper to another. So we need to optimize each time. Yeah. And basically when we increase further the temperature, then the growth rate started to increase, and even lanthanum concentration also started, so everything started to decompose at the end. So you optimize. Okay. But basically, if you see in CVD, this is a big, as we call disadvantage of CVD with respect to the physical methods, that your composition of the film is never the same as your ratios of the precursors. And this is a big difficulty, right? You put 1 to 1 and you get 20% of this element and 80% of another one. So basically what you do, you optimize the composition. And that it can take some time. It depends if you have tools to characterize immediately and so on. So you need to tune the ratio of your precursors to get to your composition which you want. Okay? But it's never you did and it's 1-1. Never. So you always have to optimize. And you see that basically it's really dependent on the precursors, and this is these two CVD systems, and we got the same ratio. Always the lanthanum amount in the layer was lower than in the solution. So we have about 50% lower amounts of lanthanum than nickel. And it's valid for both of them. So then, but basically when you have this, it is the disadvantage until you don't control the composition. But once you understood how it depends, then it means you can tune your composition from one deposition to another one. And it becomes an advantage, a big advantage of CVD. You can tune, you can add additional amount, reduce amount, and so on. So we're not stick on the target composition. And this is the big advantage. At the beginning, this big disadvantage. It takes you a long time to get correct composition. But once you know, it's a big advantage. It's a big freedom. And basically for lanthanum, there is also a problem that you have. Lanthanum oxide is quite reactive if always is carbon dioxide or water or whatever. So basically if you do, for example, aerosol pyrolysis in new atmospheric pressure, you have really a problem to incorporate lanthanum because it reacts with CO2, humidity, and so on. And you have the same problem in lanthanum-rich layers when you have excess of lanthanum. So you also need to think about the stability at the end of your oxides and to choose the correct atmosphere to do that. So yeah, so I just show very quickly the results. So basically, if you look on, first we did on lanthanum aluminate and R sapphire substrate, so you see these black lines, right? This is resistivity as a function of lanthanum-nickel ratio. It would be difficult to get such curves by physical methods. But it was not so long, it was about 5 depositions, and we did this composition dependence by CVD, right? And we see the big difference between layers drawn on two different substrates. So basically this comes more from microstructure. What is the quality of the film? Because the films were higher quality on lanthanum materials. The actual quality was higher. And basically, so when we do the annealing, and when you anneal, you increase your crystalline quality, you did at high temperature, and then you get decrease of resistivity. But if you grow directly, like in the LCD, we grow directly at higher temperature, then you get low resistivity immediately. So what I want to say by this graph is that it's not, except if there is some sensitivity to some type of defects and so on, but in general, by different methods, by different reactors and so on, you can get the same quality, the same properties. It just depends how much of energy you put in to optimize. By some methods it might be very difficult, by others it might be easier to get the same result, but it just depends on how much you put energy to get that, right? And how much you knew how to optimize that. It's not something that this method is giving better films and this one is worse films, right? Maybe your temperature was lower and your crystalline quality was not so good, and so on. But you always can get, so it depends on what kind of properties. Sometimes the methods will give you some impurities, naturally interesting impurities. Like for example, you have evaporation and sputtering. In sputtering you have impurities more by argon and so on, and it will increase your resistivity of metals and so on. So it may be dependent on the method, but normally you can obtain the same thing by different methods. There is not something more advantageous than another one. Okay, so now let's go to the CVD phenomenon in general. So we have the process parameters, type of precursors, the gas ratio, how much we send the different precursors. Then we have the deposition temperature, pressure, flow rate, deposition time, reactor geometry, and so on. always, these parameters are used to play with thermodynamics, chemical kinetics, and mass transport, which will govern all the properties of the films. Okay, nucleation, growth, microstructure, composition, stoichiometry, thickness, and so on. So all this is related, and to do CVD without understanding what is happening behind is too complicated. Okay? So each method needs to understand what's behind, and then you can control the properties of the layer. So basically what happens in CVD, so we discussed up to now here, how we evaporate, how we get vapor, and how we control the ratio of the vapor. So once we get to the deposition zone, which is hot, high temperature, right? There are two things that may happen. It may happen homogeneous gas phase reaction. So when you put your substrate in the middle, before the precursor will come out to the middle or the end of the furnace, you'll get this homogeneous reaction in the volume. So it means you form a powder. And this is highly used to make a synthesis of powders. Right? So you send the precursors to some volume which is heated, and you get powders of both sides. Or you have very high gradient of the temperature, and then you have heterogeneous reaction. It means the precursors have no time to heat up, we touch the surface and you get heterogeneous reaction. And then this heterogeneous reaction, your precursors decompose, and then you have atoms diffusing on the surface and forming the nucleus and so on, and we have crystallization. So what we call heterogeneous reaction. Okay? So volume reaction, as I said, is highly used for powders, nanopowders, and so on. So basically it depends on the composition, how much you have, the concentration of the precursors, and then you can control the powder size. Okay? If your powder is highly charged, but then it depends also on the temperature, how fast reaction is happening. So you can form very tiny particles as much as big particles. Then you can, reaction on the surface, so basically it's used mainly for the thin films, but you can do also on multi-layers. You can do nanostructures. Okay, you can grow many different nanowires by CVD. You can do a co-deposition of compounds. How we do a co-deposition of compounds? You can do by any method. It's nothing very special for CVD lab. This can be done by any method. Or you have a phase diagram. And if you go out of there is a pure compound, you get two phases. So you have two phases, right? So it's like parasitical phases, frequent, and so on. But you get two, and morphology is dependent on the symmetry of the material and so on. And also on the growth orientation. And you can do also, if you send the precursor and they form a compound which is not soluble in each other. Okay? So if you want to do these mixed layers, just check in the phase diagrams, if there exist some phase diagrams, if they can be soluble in each other. If they are not soluble, then you grow and the two phases will separate naturally because they cannot be solved in each other. Okay? So it's very simple from material point of view. You just find materials which are not soluble, not mixable at these temperatures, and then it gives you this separation of phases. And you can do also 3D coatings. So all you can do to grow CVD is quite good for conformal step coverage. Okay? We can say it's an advantage because you can go on 3D forms. But if you want, for example, to do liftoff, don't use CVD. Okay, you will never do any liftoff by CVD. Okay, it's really not adapted. Okay, but if you want to cover 3D forms, it's not the best method because we have ALD for that, atomic layer deposition, but it's quite good. And then you can coat, for example, the particles or your nanowires. You can grow another material. And here, for example, how you do this? Just put the image on the other side. You have a copper nanoparticles, and then you have a silver shell around. So how you do this? You put a copper nanoparticles, and then you send another precursor from the bottom. It's like a fluidized bed list also, right? And you have a temperature, and then it goes around the particles to the air. Then you can combine both of them, volume reaction and surface reaction, right? And then you can get composites and nanocomposites. So it means that you select one precursor, which starts to decompose in the volume, which is less stable, right? Which you want to get in the particles or nanoparticles. And another one is more stable, which goes until the surface and gets this heterogeneous reaction. So it's very important, the gradient temperature, so you need to decompose one precursor, so it's really a control of the temperature. and the next one is growing on the surface. And then you get the matrix mixed with the nanoparticles. Yeah, so basically now if we go to this, we are interested here in this public only of reaction on the surface, so in foam growth, okay, no nanoparticles on top of space. So the main steps. So the first thing is heterogeneous reaction. Then we get absorption, diffusion, nucleation, formation when the atom joins together and forms a nucleus. Of course, after reaction we have a desorption of the reaction product, right? And then we have the same foam growth. It should be thermodynamics. I don't know why it's showing crazy things, but anyway. So the first thing is thermodynamics, reaction. If there is no chemical reaction, there is no growth. Okay? So thermodynamics is say if your chemical reaction is possible or not possible. Okay? So it's the first step. So basically what we look between the difference between Gibbs free energy of reaction. So it's the difference between the free energy of the products and reactants. And the Gibbs energy is defined by enthalpy, entropy, and heat capacity. And all these type of data, but normally we do not calculate that. I just show from where it comes, right? We have many different tables and sources when you can find these data on different compounds and so on. But normally we, especially in MOCVD, we do not calculate that at all because we don't know what forms afterwards, what kind of elements and so on. So basically, if its free energy is below zero, if it's negative, we have a reaction. If it's positive, there is no reaction. Okay. And if several reactions are possible, the reaction with most negative free energy will dominate. Okay. And then the reaction rate is defined by this free energy and also the temperature. It's getting better and better. We'll go for lunch soon. Okay, so in thermodynamics, so for example, we take an example with yttrium oxide, right? It comes from chloride with oxygen and so on. So normally it's about 57, if I remember well, kilocalorie per mole. But it's too negative. It means the reaction will go too fast. If you replace chloride by bromide, then it will be even more faster. Okay, so it really depends on that. So to decrease this energy, because you want negative but small energy, not to be too fast, you add another reaction in the gas phase. For example, like carbon dioxide decomposition to carbon monoxide and oxygen, which has a positive energy, and then basically when you put it all together, you get a positive energy, so it's not good. So basically you replace chloride by bromide, and then you get minus 27. Okay, so you can calculate, and then it can be used. This minus 27, it's something that's acceptable, but closer to the zero would be better.
So does it in practice really mean that you can also inject carbon dioxide gas?
Yeah, so we can put like 2 reactions together. I don't know, this is my computer. What is this? I got it. Okay, so basically what is important? If you have low, you always need negative, right? If it's positive, nothing will happen. If you want low and negative this free energy of reaction. Then you get slow nucleation. Then your critical size of nucleus is big. It means there is a time for atoms to move and to form a big nucleus, and so on. It's very good to grow epitaxial growth and big grains. And to get big grains, it's polycrystalline, so on. Because it actually needs the substrate to define the organization, right? And then if you have a high free energy, negative high free energy, then you have very fast formation of nucleus, or even homogeneous reaction in the body. If you just energy enough, it happens very fast. So basically, or you can form the particles in the gas phase, or it will be polycrystalline layers, polar layers, bad adhesion, and so on. So it's too fast. The process has to be small. You need to take some time, always. Yeah. So the next step, so once it happens, your molecule is broken, so we have atoms on the surface. An atom has to be absorbed somewhere, right? And then it will diffuse and nucleate. So the first thing is absorption. And so we have 2 types of absorption, physical and chemical absorption. So basically, when molecule comes on the surface, it absorbs always physically, right? It's van der Waals forces. It's always physical absorption first. And if there is enough of energy, so in many physical deposition methods, we have only physical absorption, especially if the temperature is low, right? So we have just this physical absorption. But if there is enough of energy, we have plasma or something else which gives you additional energy, then we can form a chemical absorption. Okay? And chemical absorption is much lower potential energy, right? And then the molecule cannot get out. Once it's absorbed, it means it creates a covalent bonding, ionic bonding, with the surface. So it creates a real chemical bonding with the surface. Okay? And then it cannot get out. So once it's chemically absorbed, your molecule will stick on the surface and it will never leave. Because then to leave the molecule absorbed chemically, I don't know, you need to put something, if it's oxide, and put hydrogen to destroy the material, but you cannot take out it. But if it's physically absorbed, then you can get out by just by heating it and giving it a little bit energy, the molecule can dissolve. So then the next thing, atom is absorbed on the surface and can diffuse on the surface. So normally it's sitting in this potential well, right? And then atom can move on the surface. So it bumps from one place to another. So it needs to sort of jump over other atoms, right? So when atom is in this position, like in between two atoms, so it can create two links, right? So energy is lower, then the atom is sitting on the top of one atom. Because basically it can create link mainly just with one atom. So basically you have this lattice potential, moves from A to B. So it's very small difference, but it defines diffusion energy, okay, which is needed to diffuse over the surface. So it means if your temperature is low, you don't have energy to move. Okay? So when you increase the temperature, atom has more energy and then it can overcome these small potentials and to move. But normally your surface is not just atoms, you have the drops and so on, and the terraces and so on. So basically when atom moves on the surface, when it jumps here, then it can create the free atoms around. And then it's very stable. So it sticks with the free atoms. That's why we always have this terrace growth. When you have the terraces on the surface, the atoms will always stick on the side. Because it's the highest, the lowest energy. And it's very difficult for atom to move on top, because you have a lot of energy to jump over. Right. So basically the atom diffusion is dependent on the surface quality, right, and on the temperature. Because the diffusion rate is dependent on the energy, and the energy which is needed, activation energy of diffusion, it depends really on the quality of the surface, how much of defects you have. If your surface is very rough, nothing will move. It will stick immediately in the defect site and then that's it. So if your surface is very smooth, then it can move, but you need enough of energy to be able to move, right? So if you want to grow epitaxial films, if your surface is rough, you cannot do much more because it's not diffusing on the surface, right? But anyway, even if your surface is smooth, you need to give an energy to move. So it can be temperature, it can be plasma or some other, but temperature is one of the main factors which helps you to move. That's why in epitaxy you need high temperature. If no, your atoms cannot move and you cannot arrange the structure and adapt to the substrate. So when you have nucleation, so this is valid for any method basically. And what I told before, diffusion and so on is a physical or chemical method. So yeah, so it was already presented last week. We have layer by layer from the Iceland and Iceland growth and so on. Okay, so it's how we will form the islands. So when several atoms meet, they form a nucleus and then they cannot meet anymore. Okay? And the nucleus size is very dependent on the temperature. Because when atoms have a lot of energy, you imagine you get to meet 5 persons. And if your energy is low, you stick to your neighbor and you stand. Right? When the temperature is high, you come, you go out, okay? There is no problem, okay? So at high temperatures, the nucleus, they need much higher critical size to be stable. Okay? At low temperature, you meet one guy and say, okay, I'll sit here. Okay? And you sit. Right. So basically everything in this type of nucleation and how it grows, the type, is defined by surface energy. So surface energy is always positive, negative, zero, or can be positive or negative. 70% thinks that it's positive or negative. Can be both. Negative about 12%, positive 24%, 6%. Okay, so there are a lot of opinions, and I think positive or negative, and okay, we don't know exactly what it is, so we say positive or negative. This is an answer, I think, right? Yeah, 60% for positive or negative. Basically, the surface cannot be negative energy, because if a surface in general would have negative energy, it means it's very stable. So everything would like to become a surface. And everything cannot be a surface, right? So surface is always positive. And always the materials try to reduce the surface, right? The water droplet is a sphere, right? Because it's a smaller surface. Because we have these free bondings on the surface, and that's why it's positive. So it's not stable, but material has to live with the surface, to terminate somewhere, right? But so material try to reduce this surface energy by making it smaller, okay? Somehow to reduce it. So, okay, so in the case of Iceland growth, which surface energy is higher, film or substrate? You said material wants to reduce energy. So it should just come straightforward. So we have Iceland growth, the film grows on the hills, right? So far substrate is winning, but film is coming. Yeah, 65% thinks which is a substrate, energy is higher, and 35 thinks it's film energy, film surface energy is higher. So what material is doing when it's growing on a hill? It's trying to make a sphere, or trying to reduce its own energy, right? So if the substrate surface energy would be higher, the film wants just to cover everything to hide this surface, because the system reacts like in all systems in general, right? So if the substrate surface energy is higher, the thin film will try to go everywhere and to hide this high energy surface, okay? If thin film surface is higher, and this is lower energy, the system doesn't want this high energy, right? So everything goes on the top and you hide yourself, okay? So you grow in Iceland. Okay, so you reduce your own energy. You don't want to put here because it's too high energy, but at some point you start to grow and you cover everything, right? But you try to, so you're growing up, not to these sides, to reduce the energy. So we're making these balls on the surface of Iceland. So it's not so simple. I just explained in two terms, okay? I explained you in a foam surface and the substrate surface. Okay, so you have like two, but you also have interface. So basically, it's a sum. Film surface minus substrate surface. So if it's negative, I said the substrate surface is very energetic, then you have layer by layer growth. If your film surface is very energetic, then you grow to Iceland to reduce your surface. And then you can get the mixed layer Iceland growth, where you have interface energy, epitextual energy. And this can change with the thickness, which can make it go from one mode to another mode. Okay, so it's additional parameters, more difficult maybe, which can play on which type it is, because this energy is important. Okay, so this is just an example of how it grows. These islands or the nucleates, and they grow, the density increases, and the size goes up, and forms continuous form. Okay, one more question. So, in equilibrium, you have a crystal, right? And geometrical shape of a crystal is always the minimum of the surface area, not always the minimum surface of the area, independent of the surface energy, or it's random. competition between first A and B. Oh, someone thinks independent of surface energy. Good. Okay. Yeah, so 60% thinks that it's always in the minimum of the surface. Have you ever seen the crystal, natural crystal, sphere? So it's not minimum of the surface, because minimum of the surface is a sphere. And the crystal never is a sphere. Okay? So it's not always the minimum of the surface area, right? It's always the minimum of the surface energy. Okay? But not surface area. It reduces its area, okay? But it goes the planes which has the lowest energy on the top, the dense planes. Okay, the dense planes has the lowest surface energy. That's where we go on the surface. That's why the crystals has very particular shape related to the symmetry. Okay, so this is how the crystal reduces its energy. So it's not minimum surface, but it's always minimum energy. And then it's the difference between the different planes and so on. Oh, okay. Okay, so dense planes, which means you have a lot of atoms, the bonds can recombine. Dense planes, it means low surface energy. Okay? So, now we grow a thin film. If we have low growth rate, we grow slow. The film has the time to see what is my substrate, how can I adapt myself on it. Okay? So we can grow epitaxial films with different orientations and so on. If your substrate is not adapted to your epitaxial growth, and your material doesn't have a big difference between different planes, okay, because it depends really on material. Some materials has very important difference between the planes, different energies, right? Like 1-1-1 orientation of the platinum of the metals is the lowest energy and it's very significant difference. That's why you will never get a perfect polycrystalline film. It doesn't exist like in the powder, your X-ray diffraction pattern. Okay? It never happened. Because your surface energy is not the same. So if you have a big difference, okay, the planes with this, if your substrate is saying nothing what to do, okay, these planes with the lower surface energy will be more frequent, the grains with this orientation, okay, with this low surface energy. And sometimes, if we can go faster, and material don't have a time to think about a substrate, about anything what can impact its own orientation, you can get these nicely textured films. It's very easy in physical methods when you have direction additionally it grows in this. But in CVD you need to go a little bit to get speed that material don't have a time to think and it just grows lowest energy. Okay, so when you get these textured films, which is independent on the substrate, but this orientation is controlled. It's not possible in all materials, but you have to have big difference between surface energies. Okay? And then, if you have this big difference, like zinc oxide, okay, then you can grow nanowires. When you go fast, if your deposition rate is very low, you do thin film of zinc oxide. You increase a lot your deposition rate, you go on nanowires. And when you control how much you have nucleus density, you control your nanowire density. Okay, so if we increase the deposition temperature, we increase critical size of nucleus, we get longer formation of continuous layer and higher critical thickness. If we increase deposition rate, smaller nucleus, lower thickness of continuous layer formation. So basically, if you want to do epitaxial films, high temperature, low deposition rate. For polycrystalline films, we can use lower temperature and higher deposition rates. So it's always temperature, energy which we give, and also how much of material we send, and if you give a time to think on all what to do with a substrate. So basically, it's a trade-off between temperature and the growth rate. So you can attain epitaxial growth at much lower temperatures if you grow very slowly. Okay, so if you reduce your growth, your deposition temperature for some reasons, you cannot use high temperature, reduce a lot your growth rate, and maybe you will be successful. By sputtering, you can grow even at room temperature reduction. If you reduce a lot your deposition rate. Okay, in CVD, it will be complicated for your precursors and so on. But basically, you can And if you can go to high temperature, you can go faster also. So it's a trade-off between those two parameters. So when you have kinetics, I will go faster because I see there's a lot of problems with my presentation. So basically in CVD you have a boundary layer, okay? The precursor is coming to the surface, and then you have critical boundary layer, and then you have a film growing, right? So the growth rate is defined by two factors. The flux or the diffusion and transfer through this boundary layer, which depend just on the concentration difference at your interface and also in the gas phase, okay, the concentration difference. And this transfer constant, which I'll explain later what it is. And the reaction rate itself, chemical reaction, how fast it takes place. Okay, so we have like two velocities together. So basically this diffusion or transport is defined by the thickness of this boundary layer, okay, and which is defined, so the thickness of the boundary layer and the diffusion constant, how fast the material can diffuse. And this is related directly to the temperature. So you increase the temperature, diffusion is faster. And if you decrease the pressure, it's also diffusion will be faster. Because if no, you have less of collisions. And chemical reaction is limited by this free energy and the temperature, so it's chemical reaction rate. It's standard. So basically the growth rate is dependent on these both factors. Okay? So if your chemical reaction constant is much lower than the transport constant, then chemical reaction is limited by reaction on the surface. Okay? It's not limited how much material has come, it's limited how fast it reacts. And if this constant is much lower than chemical reaction rate, then it's limited by diffusion or transport. Okay? So basically if you plot a logarithmic scale of the rate, so growth rate, as a function of reciprocal temperature, right? So at low temperatures, it's always limited by surface reaction. It means there is not enough of energy to react. There are a lot of precursors around, but there is no energy to react. So it goes slowly, okay? And this part is very dependent on the temperature, right? You increase a little bit temperature, the temperature is not homogeneous, so with very different thicknesses. Because you get more energy, immediately you react more, okay? And then you have mass transport limited, in which you are less dependent on the temperature. It's still dependent, but less dependent. And it means everything that comes to the surface, everything reacts. Okay? But it's limited by how much of material is coming. And normally, so we have this first chemical reaction limited regime. Then we have more or less stable growth rate, in which you have mass transport limited, so how much precursor is coming to the surface. And normally in CVD, if you increase further the temperature, you start to get depletion, or in other words to say, your precursor starts to decompose before coming. So then your reaction rate goes down. So you cannot go a limited way your temperature to increase up. Okay, so you have this limitation, you have this depletion, and then you can get the particles inside and so on, and it's not good. So basically in CVD you can work in this regime and this. Never use this one. So then this boundary layer, so basically it's defined by the diffusion constant, it's dependent on the temperature. And then the thickness of this boundary layer, right? So this rate is dependent entirely on the thickness of the boundary layer. It's dependent on viscosity, density, and velocity. And basically when gases goes on the surface, it's very complicated to get this velocity of the gases and distribution of the gases over the surface homogeneous. So normally we need to do simulations and so on. And if your layer thickness is increasing, then your thickness of the layer is going down. Okay? So when you work in this high temperature regime, in which normally we do epitaxy, you need to be very careful on your gas distribution. Because then your boundary layer will be different, and then your thickness of the layer will be different. Right? So the growth rate, how it depends on the gas flow. So if your surface reaction is limited, it means it comes more or less material. If it's homogeneous, not homogeneous, it's limited by reaction. Okay? So at fixed temperature, it doesn't depend. Okay, your growth rate is constant. So it's very comfortable to do some homogeneous vapor. But if you have variations, gradients of temperature in this regime, then you're getting homogeneous layers. And in mass transport limited, it will be very, very dependent how much of precursors is coming. So you need really to optimize your flow rates and so on, and the geometry of your reactor and so on. Okay, so then we come to homogeneity. So in this case of this CVD, the CVD which you can charge 100 wafers or even more, the big furnace, which one you are going to use? Mass transport limited or surface reaction limited? It's 40–60%, so it's not very sure. The memory should be one slide. I just explained. Okay, so about 30% thinks it's mass transport limited, and other maybe thinks it's surface reaction limited. It is surface reaction limited because in this big furnace, right, huge furnace, you can control very well the temperature. Okay, but to make a homogeneous flow in between the wafers, it's almost impossible. Okay, so you cannot use this mass transport limited because you cannot make a nice gas distribution on these wafers, right? So you can use only surface reaction limited. When you put the big furnaces, tubular furnaces, you have homogeneous temperature everywhere, you send a lot of gases everywhere, and it reacts. That's it. And you can produce a lot of vapors in this way. Okay, so how, when we are in mass transport limited, how we can overcome these difficulties in doing these homogeneous layers? One thing is to tilt the substrate, okay, and to adapt the gas flow rate. Basically, it's difficult to see, but then it's a tilting, and then it's fast. If you send fast gas flow rate, then you can optimize the homogeneity. So if your substrate is here and the gas is coming, you tilt, and you send fast. Okay, this is one method. Then you can do substrate rotation. Okay, substrate rotation. But normally you can get something, but in radial distribution is still not good, right? So then you can adjust other things like the gas flow rate, temperature, gas density, but mainly it's a gas flow rate. So by adding some additional gas flow rate, you can also get homogeneous and rotation. So you need to optimize how fast to rotate, what is the flow of the gases, and so on. So this mass transport limit is quite complicated, but what we use for epitaxy, so it's no choice. We have to find out how to make a homogeneous layers. Then another solution is the low pressure. Because basically when you reduce the pressure, your diffusion coefficient goes about 1,000 times. And then the boundary layer thickness, it's reduced by 3 times. So basically, it's increased about 3 times. So basically when you get that your constant is increased about 300 times. So low pressure CVD, if you go to low pressure CVD, it's normally limited by surface reaction. Not by transport. Because you have very few molecules coming, very slow, very low density of molecules and so on. So it's normally surface reaction limited. And then it's very nice because you can get nice conformity, okay, on the 3D surfaces, and it will be homogeneous. But then it becomes very slow. Yeah. So then if you have a surface reaction limited, it's very good, as I showed you, when you put 100 of vapors and so on, it's very nice. But normally if you send your gases from one side of the furnace to another side of the furnace, you have a problem because at some point precursors will disappear. They will react, and so on. So there are several ways if you cannot add additional lines of the precursors. You can use the temperature gradient. So you increase slowly the temperature over, you increase the growth rate. So you can adjust that. But basically what is done normally is the distribution of the vapors. Okay? So you have the vapors, tables, and then you have the gases coming like this. So it's distributed vapor systems. Yeah, and then another solution, which is more adapted, let's say, not only for surface reaction, but we saw it was more for surface reaction when you put a lot of vapors, right? But if you want to do epitaxy and so on, you cannot do that, right? You have the mass transport limited. So then we use planetary reactors or shower heads normally. So it means that we have several wafers putting on, and we have the big wheels rotating like this. Okay? And then you have a shower head. It distributes the precursors on the top. Okay, basically. So when you can inject several gases and so on, industrial systems are very, very advanced on that. And then you can use for surface reactions, you can use for mass transport limited regime, you can go multi-layers, but it will be reduced number of wafers anyway, right? Because you cannot put 100 wafers. In this system is 42 wafers to 2-inch wafers, it's still okay. It's not so small system, right? 8-inch I think is 16 or something. I don't remember exact number of industrial system, but you can do a lot in one time, right? But it's still not 100 or 200. So there is possibility to use surface reaction we will use, but not always. In epitaxy is very difficult. Yeah. So I coming to my probably I will be more or less good with time. Coming very quickly to the composition of volatile oxides, because I saw a lot of you working with lead-based piezoelectrics and so on. So we have lead oxide, we have bismuth oxide, we have potassium oxide, lithium oxide, whatever, many friends. So what to do if we have a volatile compound? So one thing, the first one is, I didn't put in the correct order because the images were not right. To decrease the deposition temperature if you can. Then you reduce volatility. It's very, very natural feeling, okay? We have volatile compounds, reduce the temperature, it will be less volatile. But normally you don't have a lot of freedom because you want to go epitaxy, crystalline, and so on, and it's still volatile. So then increase deposition pressure. Okay? You try to saturate the atmosphere. Okay? And this is just an example of lithium niobate, lithium oxide in the film. You see it go from 5, 10, 20 torts, and it goes from 48, 46, and 49% of lithium and so on. So it usually is in the side. Then you can increase oxygen partial pressure also, because it's oxide which is volatile, not a metal. Right? So increase oxygen partial pressure, it will help you to keep it. Okay, then increase the growth rate. Then it has no time to go out, pumping up. It's also not so easy when you do epitaxy, you want to go slower. So you need to use others. Then of course you can compensate target, okay? Or precursor composition, how much you add more, what you are losing. It's easier to do than in chemical methods because you can adjust each time what you need. Okay, when in the target you did one composition, maybe it will be okay. And then if you do some annealing or something like this, you can saturate atmosphere to create this oxide atmosphere for annealings and so on. And doing growth, you are in vacuum and so on, so it's normally dynamic growth. You cannot really saturate, so you help by pressure and so on. But in annealings, you can do saturation. So this is a slide for this alkaline oxides, but it's the same thing if you think about other things. So basically the problem when you have a volatile component is that your composition will be dependent on the thickness. This is one thing. In the thin films, very thin films, you have much less of this component. You increase the thickness, you get more. Okay? And frequently, yes. So I'm finishing. And frequently, even will depend on the growth orientation. Okay, if you grow 100 or 001, the out diffusion is anisotropic in these materials. So you will not get the same composition on different orientations. So basically, in physical methods, it's quite difficult because you have one target, maybe two targets, and so on. You change the thickness, you need to readjust, and you don't have so much freedom. You have a pressure and so on, so it depends how much you adjust it. It's a little bit easier in chemical methods because you can add as much. If you need twice more, you add twice more. And another problem is very particular for lithium, but in the plasma, lithium distribution isn't homogeneous. It goes to one place. It's a light element. And then you have a problem to get homogeneous on the surface. If you're growing a small substrate, it's okay. But if you think about upscaling, then it's a different issue. Yeah. So ALD, you can grow at room temperature and so on. So it's not a problem, right? Even if it's a low vacuum. But when you need to anneal, and if you want to get a epitaxial film, annealing is never good. Because your crystallization is dependent not only on the surface of your substrate, but you can start to crystallize on the surface of your film, which doesn't see at all what's happening below, and it will be any orientation. You cannot get so high quality by recrystallization of the films, amorphous films, that's growing directly. Then MOCVD, it's difficult to control the composition because it's a very complex process and so on, but you have this freedom, okay, to add more. Atmospheric pressure, CVD you can do, but normally it will be less dependent on composition, but the quality is not so high as a vacuum. Okay, so this is just an example of lithium niobate thin film. which is grown by CVD, a CVD system, and you see this is in the red, is Raman modes, and Raman modes are directly related how much of defects you have. The thinner modes, the less defects you have, and this is compared with a single crystal, which is in black. You see we get nearly stoichiometric forms by CVD, and crystal has 48.3% composition. So we can tune finely by CVD. Probably I don't have any more time. Probably I can leave that for my next lecture. Yeah, if I have, yeah. Let's do 5 minutes for questions.
Thank you.